Just start here, recording has started. So, now these frequencies can be calculated. We say that that is n and v, no, then accordingly we say n and h and n and t, okay, vertical, horizontal torsion and number of this thing. So, for a particular frequency we are taking the margin as plus minus 5% and we will keep it all through. Now, this is no hard and fast rule that you should keep plus minus 5%. If your experience says something else, you can choose accordingly, right. So, now let me simply accept that for the vertical mode I am taking 2V is the fundamental, 2V 3V what was the notation used earlier, Vn or Vnv? Anyway, it does not make much difference. 2V, 3V, 4V, 5V,
multiples of each frequency,
6V, no, whatever is given by that, say 7V, and you have N2H, N3H, N4H, say N5H. Okay. For the time being, I am not taking the torsional frequency in this particular case, assuming that this is not a container ship, because lot many will only complicate the thing. So, I find that the fundamental frequency N2V is coming somewhere here. Now, these we will take in cycles per minute here, because all this formula directly give me cycles per minute, and the exciting frequencies also I take it in RPM. RPM is revolution per minute, so that is also basically cycles per minute. Okay. This is the trend, but this is also cycles per minute. When we say frequency, cycles per minute, it implies,
shaft RPM.
External.
No, exciting frequency.
Exciting.
It can be anything. It can be shaft. That's what I am saying. No? It can be engine. It can be shaft. It can be blade. So now, let us assume that this is my N2V here. So more or less twice of this frequency. Twice of this will be 1, 2, 3. This may be N3V and this will be N4V. Okay. Now, I have taken say 5%, so I draw a line with 5% of this value and complete this band. And I hatch it that this is not an acceptable zone. Okay. Then here the bandwidth will increase because the value is larger. Here it will further increase. Here this value is going to be increased further. larger value. If I draw here, then the entire thing is there, open-ended now. Okay, so this takes care of the vertical bands all. Now, I use a different color, though he said that you don't use it. Okay, let me use black here. Somewhere here will be N3H, and more or less twice of that will be, sorry, 2H here, N3H here, and 3 times means it will be somewhere here, and N5H may coincide with this. Okay, so 3H means this is the, there will be an overlap here. Provided the values are same. If not, some up and down will be there. Okay. Okay, so 3H, 4H, 2H, 3H, 4H and 5H have been also marked here. Now, let us try to talk about the excitation frequency. Let us first talk about the engine frequency. Okay. Now, if engine is running at 0 RPM, it will excite a 0 frequency. If it is running at 10 RPM, it will excite 10 frequency. Now, this side is the natural frequency and this side is the RPM. So, what we find, there is a 1:1 ratio. If we are using the same scale, okay, then it is simply you draw a 45-degree line from here and you say that this is engine frequency. If it is 1:1 gear ratio direct drive, then this will be also shaft frequency. For direct drive. Okay. If suppose you have a gearing ratio between the shaft and the engine output, and the gearing ratio is say n, then the shaft RPM will be n times the engine RPM. Usually you try to step down.
Step down.
Usually you will step it down. Okay. So, in that case, what will happen?
It will go up.
Frequency will be in a particular ratio.
It will be down, because for say 10 RPM of the engine,
It will have 7 RPM.
say if the gearing ratio is 1/2 or something, so it will be
0.5, yes.
0.5. Okay. So, usually for ships, when you have the gearbox, the shaft RPM will come down. shaft frequency for geared case. Okay. In majority of the cases we have direct drive, or we have now gearing ratio. No, but what is the major trend?
Presently,
Direct. Okay. So, I will also present that. I will keep it based on this line, not on this line. This is only for clarification. Now, if you have a 3-bladed frequency, a 3-bladed propeller, then the shaft frequency times number of blades, 3 blade, will generate your blade excitation. Blade excitation is shaft RPM multiplied by the number of blades on the propeller. Okay. So, if you have 3 times, then it will be this. So, I say this is 3-bladed frequency. But seldom we have 3 blades, we have 4 usually. So, 4-bladed, it will be still higher. We will also have a provision for 5-bladed. So, let us have 5-bladed also. So, now this diagram which we are seeing here contains the engine frequency or the shaft frequency here, and 3-bladed, 4-bladed, 5-bladed. Okay. Now, you have proposition for say 3 engines available with you, which meets your output requirement. You have to only select the engine RPM. Now, say one engine has got, I am just putting arbitrarily here, is this RPM, which is say N1. First engine having RPM N1. So, I will see that whether it excites any frequency or not. You see, this is the RPM. So, when this engine is in operation, if suppose you put this engine and this engine is operation, this will have this RPM as excitation, and if it is direct drive, this is the shaft RPM also. So, as far as the engine frequency and the shaft frequency is concerned, it is clear, it is in the clear zone, not in the banded part. If it comes in the hatched part, it is not to be accepted. If you come to this point here, it is clear of the 3-bladed frequency. Come here, the 4-bladed propeller, if you put onto this to get the output, then it is likely to excite 7-noded vertical this thing and 5-noded horizontal vibration. Beyond that I am not considering, so 5 also it will be clear of, okay, because that I am not giving importance because of my guidelines. It is not that it will not be there. Now, so if this diagram is to be adhered to, then outrightly I have to reject this particular number of blades on the propeller. So, if I am going to accept this engine, then this engine has to be accepted with either 3-bladed propeller or a 5-bladed propeller. Okay. Now, let us see another option of another engine. Obviously, when you choose engines which will fulfill your horsepower requirement or power requirement, their RPMs also will be more or less close by. Okay. So, let us say that I take another engine which also meets my power requirement. So, having a RPM of N2. So, I try to put this. Now this engine happens to be a very dangerous engine. You see, shaft RPM, engine RPM, everything is in the one of the lowest mode RPM, vertical vibration of 3 node. It will be contained there. It is going to excite that. And then of course it is clear of 3 bladed, but 4 bladed it is just clear. If I consider that, no, if this band is closing here, it is just clear. Okay, and therefore this is absolutely not suitable. Let me take another engine, which I say is N3 here. Let me see. I am just taking arbitrary values. You see, this is N3, clear of the shaft and engine. It is getting inside this 3 bladed frequency, but it is clear of the 4 bladed. Now when you are having a single screw ship, you normally go for a 4 bladed propeller. Okay, that is what we are interested in, and therefore this engine is the best of the lot. This is giving you the best combination. Another thing is to be seen that when we say that we are putting a particular system on a vessel, we always have a life of the vessel in our mind. We usually say that ship is going to be operative for say 20 years, and quite likely that in 20 years till lifetime you are not going to change the engine also. You will only repair and run it. Rare chances that you will change them prime mover. Now what happens? Due to its own wear and tear, there will be a power drop, and the engine will get adjusted to that drop in power by reducing the RPM also. So automatically there will be a reduction in RPM. So now what we have to see, if we find a particular RPM, say for example this from that point of view, this is the thing. Now if it drops down, it will drop down here. If while dropping down, you have to see from your own experience that how much the RPM can drop down. Okay, what is the loss of power, and for that loss of power what will be the drop in the RPM. So you have to travel along with this, whether still it comes under this band or it is still clear of the band. If for that lifetime, considering the drop in power and the corresponding drop in the RPM, if it is still clear of any frequency band, accept it. Okay? Say for example, if suppose this engine by any chance was selected for a 3 bladed propeller and there is a drop in power, then this frequency will come down straight away here and try to excite this frequency here, which is one of the primary modes, 1, 2nd, 3rd mode of horizontal vibration, and the ship will always vibrate. Okay? So this particular blade will excite this frequency, but here you see, if this drops down, it is clear of this. If you select this, this is also clear of that for that corresponding drop in the power, and therefore it is okay. Right? Any doubt regarding this?
So that particular range would be called the critical RPM.
Which one?
That particular bandwidth when the RPM
No,
keeps dropping.
no. Actually, what we are trying to say here is that even if this drop is there, then it is likely to excite this, but it has to be clear of this. So if it is clear of all this, nothing is critical here.
But so these assumption that how much power will drop, it will come in the zone. Exact assessment?
No, you as a marine engineer will have some data in your shipping company, and you can, with whatever logbook will give you.
In fact, with experience also, when we feel the vibration level is increasing, so we try to adjust the RPM on the engine. It is not that within that range only.
No, it is all depending on the thing, because it's when you are going say full ahead.
Maybe this M which we are talking about, these are the MCRs.
No, I am not talking about MCR. I am saying that the operational RPM.
Operational.
You may even operate the vessel at 80% of MCR, 85% of MCR. You see, it is all your policies. Suddenly, when there was a fuel crisis, one of the shipping companies, I don't know whether it is SCA or something, they decided that let them operate all the ships at 85% of MCR. By doing so, maybe that you will save some 30% of fuel cost. 85% MCR may reduce your speed by say 10%, but you may save 30% of the fuel cost, because that goes up like that. If you see the performance curve of an engine, you will find that there is an optimum speed, and after that it goes in a parabolic fashion or exponential fashion, whatever it is. It is not linear. Okay. So, if you try to cut down the MCR, so what I am trying to say that all this RPM and the engine RPM what we are talking about is whatever is the operating RPM. If you are designing a vessel to operate at 80% MCR or 85% MCR, then this is 85% MCR RPM. If you say it is 100% MCR, it is 100%. And if you suppose decide to operate a ship at 100% MCR, and you are also ready as a company that in case if the fuel prices go up, you will reduce it. Now our fuel prices are fluctuating. Okay. So, if suppose it increases, and you say that if it increases beyond this particular level, then we will restrict our consumption to so many this thing, so that our fuel bill does not increase. So, that what is that percentage of the MCR will be known to you, and in case of emergency, if you have to overload your engine, say 110% of MCR or whatever it is, overload condition. I think overloaded condition is for 4 hours or something, isn't it? 10%. For a continuous operation of how many hours? 4 hours?
No, not 4.
24 hours?
No, 1 hour.
1 hour.
1 hour. No, usually the machines are, I think, designed for 4 hours.
But engine, I think it is 1 hour continuous rating.
Continuous.
I mean,
Overloaded, I think, is
overloaded 1 hour.
overloading, I think, can be done for about 4 hours. You may use it for 1 hour, but I suppose. Huh?
We are recommended to overload.
No, you are recommended is a different thing.
The manuals normally talk about that.
Manual nowadays talk about 1 hour only. Okay, if it is one,
We'll check, sir.
Maybe
it doesn't make any difference. So what I am trying to say that 1 hour is also a long enough duration, okay, for continuously operating at say 10% overloading condition. Now what is the RPM at that, and what is at 85 RPM? So this is the operating range is also there. So when you are selecting the thing, you must try to get a band here also. Full band. So that means the overloaded condition and also say 80 or 85% of the MCR. And then you check with the upper limit and the lower limit that all these frequencies which can be generated due to this excitation is avoided. It becomes a little complicated, but anyway, that has to be.
is to stay out of those bands.
Yes. It has to be in the clear space. So if you are in the clear space during the operating conditions, vessel is considered to be safe from vibration aspect. Of course, there are other aspects which we are not going to consider. How to select an engine? You may have selection criteria, weight is one of them, space is another one, fuel consumption is third one, price is the most important one, then maintenance, spare parts, reliability, and after the price, I think the most important is your political connections. Okay, many a times you reject a very good engine because the spare parts are available from a country with which you don't have a friendly relationship. Spare parts are produced by those countries from where you don't have friendly relationship, and therefore you can't maintain the engine. So you simply reject it. Okay. So number of considerations are there, we need not go into that. Any doubt here? Then we can see.
So that means at lower RPM you get five blade couplers.
No,
Zipping.
no. Who says?
Suppose our operating range comes down, then so will be. We may cross here.
You may cross in the very lower
lower
range.
side.
Here also you can cross. What is there? So what you have to see from here, that which combination gives you the best flexible design, and accept that. Okay. Now here what we are trying to do, we are taking the band, and even an error in the calculation we are avoiding it. But the decision which we are taking here is going to be a final decision. You have decided here that this engine you want to use with this particular blade, number of blades. Actual design will take a little later, but this engine is fixed here.
Is this the sole criteria for deciding the number of blades that the propeller is going to be?
Yes.
Initial criteria.
No, it will be final also. You have to design on this basis now.
But sir, can't we do little bit of vibration control methods
What control methods?
like dampers and other things?
Hmm.
And then you go for a
Whatever you want to do it here.
So, but engines now they have these damping methods. Then it will come down a little bit. I think if you damp it a little bit.
Now how are you going to damp it?
So in the engine itself,
Now how are you going to damp the engine frequency?
because we bring down by this what is that? I forgot. Detuners we put in engine for getting away with the second order vibration for the engine itself, which goes to the ship shaft.
Now where do you put that? In the
In
fuel?
the engine itself, sir.
In the fuel?
In the engine itself. No, sir. In the engine itself.
No, I have not understood what you are talking about.
So the vibration of the engine is brought down
How?
by using these detuners, sir.
Now what are these detuners and
So
where
there
it is?
silicon field things which brings down this natural frequency of that which comes into resonance. Suppose the critical RPM comes in.
No,
such
but
a way-
how can you change the natural frequency of a structure by using something in the engine? What you can do is
for the
the engine RPM. The structure is a different thing altogether. How can you change the structural properties by using something in the engine?
no, but the frequency is dependent on the structure property as well as the mass.
Huh.
So you can always play around with the mass. That is what we do.
Mass of what?
Mass of the moving part.
No. Natural frequency of a structure is a function of its stiffness and its mass distribution.
It's
Structure.
mass distribution.
Structure, not the moving parts. Moving part is a different thing, that is excitation.
So it's mass distribution. So you can always change the mass distribution by fixing some mass on the part. I mean,
What you can do is, you can only change the excitation properties of the exciter, not with the structure. Unless you do something with the structural properties will remain as it is. What we are talking about, this is the structural properties and this part is the exciter property. Okay, you can play about here, I don't disagree, but this part is already built as a structure. So at this stage we are checking these two together. Okay, we assume that as per the classification societies as per the usual shipbuilding practice, you are trying to design your structure and then these are the estimated frequencies. Okay, but this has nothing to do with the excitation. If you do something with the mass distribution of the exciter, then the excitation frequency will be different. Okay, if you say that instead of N1 it may generate N2 or N3 or something like that, but that is an excitation, nothing is happening here.
What they're contemplating is the natural frequency, what has already been finalized, if there are some added frames and beams,
No, they are not saying that.
I mean, will it change the natural frequency?
Definitely, definitely. That is the design part of it. I have already said that when you are taking a stiffened plate, say for example, consider an engine room where on the tank top you are putting the engine. Let us say on the tank top you are putting the engine, directly on the tank top. Obviously below the tank top, below the engine you must have the girder. Okay, girder has got certain scantlings. Now if you find you have designed that girder to take the load of the engine. Now from a frequency point of view you find that that is giving you some sort of a stiffness. By changing it by say thickness another 1 millimeter or 2, you are not going to increase the weight of that particular double bottom structure much, but you can definitely change the flexural quality or the property of that particular structure, which will directly influence the response. Because I is being changed, I is being changed. So as soon as you change the I, the frequency will change there. The mass is not increased much, but being a vertical girder, it will dramatically change the moment of inertia. So the K is changed, K is EI by L cube. You are not changing E, you are not changing L, but you are changing the I value. So I is changed, M is changed little, but the final effect will be it will change the frequency. Or in that region you change the stiffness spacing, that will again dramatically change the flexural property. Okay. So that local adjustment can be done. We are not talking about that. I suppose he is also not talking about that.
You had said this side is already finalized and fixed.
This side is finalized in the sense this is a structure part, this is the engine part. We are trying to now decide which engine to be put into the ship. So first assumption is ship is there. So if the ship is there, these are the natural frequencies. Now which engine is to be put? Now what excitation you are going to put into that? So this is what we are deciding. If you find that out of these alternative nothing is fixing, maybe that you have to change the entire property of the entire design of the ship, because this is still at the design stage. We are using those approximate formula only at the design stage. I have already said that you are making a bid now. Nothing has finalized. So when you are proposing something, you may say that to the owner that why are you selecting this length, this breadth, this depth of the ship? Change it. Change the mass of the ship, change the size of the ship, whatever it is. I will give you a better ship, because you are going to design. You said that why are you interested in say 130 meter long ship? Why not you go for say 145 meter long? Is it going to make difference to you? If suppose the route which he has given, there is no length restriction, okay, will it make much difference for him to, obviously with the length his dues will increase and so on and so forth, but as a designer you will do an economic study of that and you will try to tell him that the size which you have proposed and the size which I am proposing both have the same economic value, maybe that your proposal is more profitable than what he has proposed you to design. Okay. So that team will say. Is this part clear? So at this stage, this is what is the Hull resonance diagram, and this is the importance of it, and we cannot do away with this part. Okay. Now once we have decided about this, and then we would like to find out or redraw the Hull resonance diagram when the order is already awarded to you and many of the structural items are known to you. So at that time, majority of the structural arrangements have been done, and as a classification society they try to approve certain major drawings, not the construction drawings and the details, but the major scantlings. Those are all approved. So based on that, you try to finalize what is the basic structure. So we try to do, I am saying that Hull frequency calculation. Now, this is a detailed method where you actually use all the design particulars of the ship. We have seen that for every section of the vessel, first of all, let us say that we have seen that hull is considered as a girder. So, when we say hull is a girder, then it is basically a beam. It is floating freely in water and therefore, the end conditions are free. Okay. So, for the vibration case, we assume a ship girder to be a free beam. Now, we have also seen the basis of this Schlick's formula or the Todd's formula, which says that EI by delta L cube. Now, EI by L cube is a function which defines what is the stiffness, and delta is nothing but the mass. So, if the ship is broken up or is imagined as a member, so let us try to consider the ship first and then we will talk about it. Say this is the ship I am considering, floating in water somewhere here, and I want to divide it by a number of sections. Okay. Now, I say that this part of the vessel between these two sections will be represented by a particular mass, and that mass is somewhere here, center of this. Similarly, this particular part is this mass, this particular part is this mass, this particular part is this mass, and so on. And they are interconnected by some sort of a spring, which has got a stiffness property which is nothing but at this section, because this is the midsection of this. So, at this section whatever is the sectional properties E, I and L here. So, based on this, this will have some stiffness. Okay. It is a continuous system and therefore, I can imagine lot many such point masses. What is this mass? This mass is the mass of this part completely, hull and cargo, any other mass which is being carried within this space, and then we also talked about added mass. So, we add the added mass of that. And how the added mass is calculated? We know that this is the cross section, so underwater cross section is known, and we try to find out what is the CV of that, and then we add it. Okay. So, here that calculation of added mass will come into picture. So, to find out rest of the properties, you require the shape of the vessel, right. So, the lines plan which has been done for the ship, now we are coming to the detailed calculation. So, lines plan is now available, and from the lines plan I get a section shape here. So, I get the exact B, I get the exact D and B by D ratio or whatever it is. So, I can find out what is the added mass coefficient of this particular section here. So, that is, so the added mass is added to this complete thing on the basis of this added mass coefficient spread over this distance. Okay. So, the mass of the ship plus the added mass of the ship, these two together move up and down, and when it moves up and down, then the flexural vibration will either take place like this or any other mode. So, assuming this to be a harmonic oscillation, this displacement will have the corresponding acceleration, because it's a to and fro motion. So you have the displacement, you have the velocity there, and you are having the acceleration. Now with this acceleration, at every point you can find out what is the acceleration up and down for this movement. What is the acceleration at this point for this movement? Now this is corresponding to some mass here, and therefore you are getting the acceleration of that particular mass, and therefore you are getting the inertia force of that particular mass. Okay. So now this inertia force is going to give you some sort of a loading onto this beam. So now I am bringing back the concept of that a ship is loaded by some sort of a dynamic loading, which is mass into acceleration, and if you have the rudder which is loaded by this dynamic force, then integration of that will give you some sort of a dynamic shear force. Integration of that along the length will give you something, dynamic bending moment. Divide that by EI value, flexural rigidity of that section at that particular cross section, then I get m by EI curve in the dynamic bending moment. Integrating that, I will get the dynamic slope, and integrating that, I will get the dynamic displacement. Okay. So this dynamic displacement will give you some sort of a dynamic acceleration, and that is a time dependent function, and from there you can find out what is the frequency. I am starting with some sort of a deflection pattern, and I am arriving at a deflection. Okay. Now the starting deflection pattern, if it matches with the derived deflection pattern, that means what I assumed earlier, that the ship is moving in this shape, is the correct shape. And if it corresponds to this derivation, then my assumption is correct. If not, then I have to modify this. Ultimately, the displacement to start with, you should get the same displacement there. So this becomes an iterative process. You start from here, go there. So you have assumed something, you have derived something. If the assumption is correct, then the derived thing should match with it. If it is not, then you have to modify the assumption, and then again you try to derive, and keep on doing it till the starting point and the end point are acceptable to you within the engineering accuracy. Is that clear? If that is okay, then what we do, we make a chart here. Column 1, as usual, we say serial number. Or station number here. Column 2 is the mass. Column 3 added mass. Column 4 total mass. Okay. Now we are talking about mass, but actually what we will be doing is we will take the weight, because this part we say that the weight of this portion is so many tons. That is already there in our head, and I do not want to change that notation. Okay. So to get the mass from that weight, I have to divide it by g. Now instead of that, I know that I have to divide it by g. Even the added mass, I should get it in that. So what I will do, instead of mass, you just take weight here and correct it to weight here, and then we take total weight. So what happens, g is included here, and then I will say that added this total weight is a representative of the total mass. Okay. So, weight is a function of mass, g included in it. Then you take assumed displacement. Okay, we take some assumed displacement. So, now you can take this as an assumed displacement for a free beam. So, normally what is done, you take a uniform beam, and for the uniform beam you consider a free beam displacement curve, knowing fully that ship is not uniform cross section, or it is not a beam of uniform cross section. But my first approximation, you have to start somewhere, and therefore we take a uniform beam's free curve. The displacement curve of a free uniform beam is the starting point, usually, right, which is symmetrical about the midship. You can also start, if you have already done the longitudinal strength calculation, then you have the static displacement curve. You can even start with that. If nothing is there, you simply assume that all displacements at all stations are unity. Okay, there is nothing wrong with that. Only thing, your iteration will take more time. Then total weight into the assumed displacement, because I assume harmonic motion, and therefore x of t, x double dot t is given by minus p square x of t. Okay, and mx double dot is the inertia force. So, if I want mx this thing, so it is nothing but p square mx, right. If p square x is a function is equal to x double dot, then inertia force is equal to minus p square mx. So, my inertia force I will calculate on the basis of mass into displacement. It's okay. Or dynamic loading. Right? Then you have 7. Integrate this along the length, you will get your dynamic shear force. Integrated once again the shear force, you will get dynamic BM. And then at all these sections, you know what is EI, or simply I of the section. And then you try to find out what is BM by I. This divided by this is equal to this. Okay? Try to integrate this, you will get dynamic slope. M by EI, I am not taking E here because E is constant also, so why unnecessarily do that calculation, I will do the calculation towards the end. So, M by EI curve is there, integrate it, you will get the slope, and then integrate this, you will get dynamic displacement. Okay. If your assumed displacement is correct, if this is the mode shape, if this is the mode shape, then this and this should match. If not, bring column 12 to column 5, repeat all this calculation and keep on doing this till you are satisfied. It's a very difficult job, time consuming. So what is done here, that the assumed displacement is assumed as a fraction of the maximum displacement. Okay? It is assumed as a fraction of the maximum displacement. That means wherever you are taking the maximum displacement, that is unity, and remaining are all fraction of that. So here also, whatever the dynamic displacement you get, you try to normalize it by dividing all the rho values by the maximum value here. Okay? And then you are going to get the normalized value, and then you try to compare it. So what is happening here, we are starting, if you are taking the unity here, we are not bothered about the absolute measurement, but maximum value. That means we are starting with a particular pattern, and we are not changing the pattern, we are only trying to change the distribution of the zone. So we are getting the same pattern here, maybe that it will get rotated here or it will get deflected like this. So we are modifying this pattern. And as you can see that we have assumed this function, so p square is included here. Okay? So in this part itself p square is there, and we have to take it out from this expression here. We will take it up in the next class. Once again, on Wednesday we will try to give you the detailed part of it. Okay? Any questions here?
We are not considering the buoyancy forces.
No, mass distribution.
Only
No
mass
buoyancy.
distribution.
This is for a floating ship we are doing, sir.
In a similar way we are trying to do it. So actually what we are trying to do here, the number of stations which we take here, where we are considering the number of masses. Okay? And that is what I was saying, that it is basically a multi-degree freedom system, and depending on your computing capabilities, if you are doing it physically, maybe that we will take only 11 masses here, as we do for the line spline. But if you have a PC available and somebody to feed in the data, then why this much? We can take actually at every frame space, or
Actual frame space.
actual frame space, because all those data is available with you, right? So actual frame space we can take, and that may work out to be, say, every 800 millimeter. So instead of 10 or 11 sections, this will be 130, 140. Or if somebody is interested, he'll say, okay, I'll take it every 10 centimeter. You can even take 1000 divisions here. So more you take, more continuity, or more towards the continuous system you are going. Right? So if you have a machine which will try to calculate it automatically, that value, these days it is not possible, not impossible. You can give at discrete values, and then you can make it uniform, or you can get the distribution curve, pick up the values at any desired level, and all these calculations can be done. So if that can be done, this can be repeated also. There is no problem. You just give a check value here and you say, if it is not, go to this, repeat this. And if it is available within the accuracy level, you say stop.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.